SwayamPrabha. Digital India. Educated India.
Good morning, welcome to the NPTEL course on architectural acoustics. This is the last lecture of the second week and this is on the application of reverberation time. So, this lecture will end the second week and this whole module of the room acoustics. So, in this lecture we will try to do the application oriented the version of the reverberation time. If you remember, in the very first two lecture we are discussed about the various fundamentals of the room acoustics by Dr. Gupta, and then the following two lectures I have discussed with the sound absorption coefficient first and then the reverberation time and concept of the reverberation time. So, today my goal will be, or the objective will be, we will formulate some procedure to obtain the reverberation time for any enclosed space. So, we will go very step by step way how to formulate one after one, and finally, the aim is to get the RT. And also we will going to interpret the necessary changes of the parameter to achieve this required reverberation time. So, what will be the significant change? So, if you know this formulation, this step by step formulation, then suppose in the second step what can be changed to get some effect on the last, and that kind of interpret this particular the formulation of the necessary changes in the parameter we need to know. So, here let us again go back to the Savin's equation, which is given as that RT is equal to 0.16 V by S alpha. I have put a summation sign because it is summation of the S alpha, the sum of the various surfaces and its product of the absorption coefficient. Now, let us draw a graph. This graph is based on the volume and the total room absorption. The total room absorption is S alpha, this summation S alpha. And if you see in this particular this equation, or I may go to a blank page. In the blank page, so it is the RT is equal to 0.16 V S alpha, which is summation. So, this is the total absorption. So, I write capital A and this is 0.16 V. So, if I say this as the A is equal to now 0.16 times RT multiplied by V. So, this is give you a kind of a equation which is a equation of linear equation where A can be represented by x. This is some slope of the equation and this is x, y equal to mx kind of thing. So, I will get a straight line equation as I know from this particular way, this is going to be. So, I will, if I plot this A in the x and sorry, A in the y and this V in the x, I must get some line like this and various lines because of the various combinations of the RT. So, I got those lines. I got those lines over here, and those lines are actually this green line is actually for the RT is equal to 1.5. So, and these blue lines are RT equal to 0.5, the red is for 1. So, as the RT value is changes, the line and slope of is also going to change, and as the RT value is decreasing, this slope is increasing. That is one of the major the observation from this particular graph. Next, Let us go to the another empirical formula where the RT can be calculated by virtue of some volume. So, after this Sabin's equation, lot of physicists actually go into calculate the RT, and this RT value is not going to be fixed for the same different type of performance will require different type of RT. So, various physicists actually work in this arena, and some of them has some come up with some formula, the some kind of the empirical formula. So, this is one of the empirical formula where RT can be projected by this, and here the V is the volume of the room and K is a constant, and this K is based on different type of performance. So, suppose if it is a speech, just like this particular the lecture room is for speech. So, this K is 4. Suppose it is an orchestra where there are some instruments, some singing and all, it is 5. Suppose if it is a choir kind of a thing, where is a group song in a kind of a thing, then it is 6. So, again by virtue of this V and RT values, the RT is kept in the y axis and the V is volume in the x axis. Again you can plot for different volume what should be the proposed RT value. So, we can see the green one, which is for choir, which is higher, and the speech, which is blue, which is lower. So, for the speech you require some low value of RT, for a music you require little more. So, let us go to a kind of a band where we can see the what are the different standard reverberation time for different space or different performance. So, there are 5 such classification, room characters classification, very soft where the RT is very low. See, the RT when it is 0.2 to 0.25 second, it is actually required for the recording studio, the TV studio, for the radio or any kind of broadcasting cases. Suppose any television broadcasting where there is a speech, any commentary box for any sports arena, you require very low RT value 0.2 to 0.25 second, and the mean absorption is almost 0.4. So, you have to put lot of absorber and that 0.4 has to be achieved. The soft is 0.4 to 0.5, the RT value in between 0.4 to 0.5, it is for the theatre where there is again there is a speech, there is lecture hall just like this is a speech, restaurants and all. The most cases are normal cases, which is 0.9 to almost 1.1, where it is cinema hall, the office buildings, the library, the multipurpose auditorium, residence etc. are in a normal category, where the mean absorption coefficient is almost about 0.15. The herd where the reverberation time is little more is 1.8 to 2 is church and the hospitals, and very large is the factory and the churches 2.5 and 4.5. You see the church and the religious place, you always require the very high RT value. So, perhaps you have already learned the classical architecture and the history of architecture. If you go to the history of architecture lecture and the books, you see all the church in the European church are very high in volume, and also it is having very hard surfaces. The church required very high RT, not only church, any sort of religious song and religious deliberations is actually demand high RT value. It may be a bell of church, it may be some singing in the temple, it may be some kind of a beating of drums in the for the monastery, Buddhist monastery, or maybe it is the azan in the Islamic the mosque and all. So, you required all there is a prolonged version of the sound which demand high amount of the reverberation time. In other sense, when it is a speech which is recording studio or maybe theatre or lecture hall in this particular domain, you require a very discrete and concrete and very split of sound. There should not be any prolonged kind of a case, then there will be kind of the hearing problem and the intelligibility problem and the kind of the confusion will create in time of hearing. So, let us next stage, let us try to calculate the how the reverberation time can be calculated, what are the steps, what are the formulations. So, I have drawn a plan of a hall of 30 meter by 15 meter and the height of the hall is 6 meter, which is given in the section. And this hall is having 4 doors of 2 meter by 2.5 meter and 3 meter by 1.5 meter, 6 windows, which is plotted in this plan in blue color. So, first what we will do in the very first step, we will first find out the what is the interior area. So, we calculate the door area as 20 and the window area as 27, the ceiling is 30 by 15 is 450, floor is also 450 and wall area I calculate the perimeter and I multiply the perimeter by height 6 and I deduct from that 20 plus 17 because that is the window and door is in the part of the wall. So, 493 is the total wall area. Total wall area and the volume of the hall is 15 into 30 into 6, which is equal to 2700 meter cube. So, first you calculate all the surface area, then go to the next and try for the next data that is given for this particular. So, what the next set of data? So, next set of data is given as the door and window has glass and aluminum, which is having alpha value of 0.01 because this is very reflective. The ceiling and wall is also very reflective as 0.02, it is plaster and the floor is wooden floor is 0.12. So, if you see all the 3 materials what I have given as a part of the problem are mostly reflective material. The alpha value is very small, very close to 0 for the first two and 0.12 for the floor. So, I am expecting a very high RT value for this room. Then I start calculating the next stage where I multiply this alpha value with the corresponding area and I am finding the total absorption of that corresponding area by meter square 7. So, I have multiplied everything, ceiling is 0.02 and the floor is 0.12, again wall is 0.02 because both are plaster. So, and I add all these 5 and then I got a total absorption is 73.33 meter square 7. So, my second the stage or the formulation is over. So, now I know what is the sum of S alpha. I also know the V. So, I can calculate the RT now, but let us go to further some character of the room. Suppose this hall is having a capacity of 300 people can sit and listen something over there, and there are 2 options. Suppose there is a cane chair or maybe a cushion chair like this cushion chair, and there is the audience also. So, I have given the per seat what is the absorption. Cushion chair is 0.5, cane chair is 0.01 and audience is 0.4, and by virtue of the clothing and all these things, the hair and all, you have the kind of the absorption per human being also. Suppose this is summer cloth, so it is having a absorption coefficient less. Suppose it is in winter, if I having a jacket or maybe some kind of a woolen, my the audience absorption per audience absorption will also be very high. So, what happened is that now I go for the third calculation for the absorption for the chair and all. So, only cane chair if I use, then it is this much because per chair is 0.01 and there are 300 chair. Only cushion chair or no audience is, if it is there, then it is 150, and if the audience is full, I mean there is a full audience, then the 300 audience per audience is 0.4, this is 120. So, either it is a full house or maybe it is empty or maybe it is half full. So, some conditions will be there, and based on that I can take the permutation combination and then I can again find out some amount of absorption. So, what happened in case of there is a empty hall. So, if there is a hall is empty, there is no audience and I have only cane chair which is very reflective in nature and there is no absorption at all. So, the total S alpha value will be 73.33 plus 3. Why 73.33? That comes from the absorption of the surfaces, and why this is 3? If you go to the previous slide, if it is cane chair, no audience, it is 3. So, total absorption is 76.33 and the RT value by virtue of your volume and 6.33 and 0.16 is 5.7. I predicted that. I told that if there are less amount of absorption and there are so much of reflective surface, I am going to get the high reverberation time, and I am getting that, and this hall is empty hall, no audience. Now, let us see if I replace the chair, cane chair by cushion chair. So, 73.33 will remain same, but 150 comes from this cane chair and no audience case. So, this 2 gives me 223.33 as the S alpha, and finally, this will be my RT value 1.9, drop down 5.7 to 1.9, it is improved. Now, let us see if it is full house, it is full of people. So, all chairs are full of people. So, the audience is now going to absorb. Then this is 120 is for the full audience and 73.33 is give me 193 and the corresponding RT value is 2.2. So, you see if there is a empty hall or maybe a full house, or if it is a cane chair or some other type of chair, it is also impart a physically the RT value of a room. Now, let us take a design base case. I am going to design this particular room for a base case, where I am going to use the cane chair and the half the hall is occupied. So, that means the half the hall will be occupied and rest half is cane chair, and this will be my base design condition, and for that I want to set up a particular the design the RT value. So, for that I recalculate the what will be the empty chair condition. So, 150 empty chair with 1.5 absorption and the 150 people will 0.4 equal to 60 is the meter square Sabin. So, total is 61.5, and for that condition the 73.33 remains same, surface I have not changed. So, finally, 134.83 and it gives me 3.2 reverberation time. And please remember, this 3.2 is my base, I want to improve it. Improve it means reverberation time improvement means you have to reduce the reverberation time. 3.2 is too much. Suppose this hall is for speech, we require almost 0.6 or so. If it is for music also 1 second or 1.2 second like that. So, 3.2 is something like a church. So, this cannot be actually taken. So, I have to improve the other surfaces. So, I have first case as I will do some covering, I will cover the door and window by heavy curtains having alpha value 0.65 and the wall will be treated with the absorptive tiles having alpha value point. So, I have taken these two decision. I will treat the wall and I will treat the door and window by virtue of some the curtains, but the ceiling and the floor I will not going to treat, that will be as usual as earlier. So, if I do that, I have taken the same the calculation table from the previous. So, door is now a new way I have to calculate it. The 20 will remain as 20, the area has not going to change, but instead of this wooden door or that glass door and the glass window, now there is a curtain. So, 0.65 comes from here and this is got cancelled. So, the 2 meter square Sabin which was earlier is now 13, it is improved. 2.7 for the window is now improved to 17.55 by virtue of induction of these two curtains. Ceiling and floor I told I will not going to treat. So, these two remain same 9 and 54, but wall is now going to change. What was earlier? The earlier was it is the plastered 0.02. Now, I have treated with that the wall with a sound absorptive tiles 0.45. So, this 493, the total area of the wall was multiplied with 0.45 and 9.86 is improved to or increased to 221.85. So, total Sabine, total amount of Sabine or the meter square Sabine, the total amount of absorption of the room was 73.33, now it is 315.5. So, definitely I am expecting a low version of or the low RT. Let us see how much is the RT. So, cane chairs and half audience gives me 61.5 and this 315.4 from the surfaces, total is 376.9. You see earlier it was 3.2 and this is 1.15, much more control was achieved. But if it is in for speech, if it is for music, for some kind of a musical performance 1.15, or if this hall is for some movie or the cinema, it is okay. But if it is for speech, for any kind of lecture room, it is not, still now it is not suitable, it is too high. We have to come down to 0.6, 0.7. So, I have a case 2 also. So, in case 2 what I did? I remain these two as it is, curtains in the door and window, sound absorptive tiles in the this wall 0.45. What I did here is that I created a suspended ceiling with some tiles of alpha value 0.3 and I hang this particular ceiling at a depth of 1 meter. So, what I did? I did a new surface, I put a the suspension ceiling at a depth of 1 meter from the structural ceiling soffit, and that gives me two benefit. One is I also treated that particular surface with the acoustical tiles of 0.3. So, the surface which was plastered was hidden now and the absorption coefficient is also increased, and the second one is by virtue of lowered down the ceiling, I decrease the volume of the room also. Now, you see in the volume of the room has to be calculated as height 5 meter, not 6 meter, because 1 meter is actually taken by the suspension ceiling. So, let us recalculate the volume 15 into 30 into 5, which was 2700 earlier, now it is 2250, and the new surface of the wall also will decrease, because the 1 meter band in the roof, which was now hidden by the suspended ceiling, has to taken out from my calculation. So, now the perimeter is multiplied with 5 instead of 6, 6 was earlier, now it is 5, because this portion is exposed to the sound and 20 plus 27 is the door and window was deducted. So, now new the area of the wall is 403. So, based on this new to volume of the wall, volume of the room and the surface of the wall, let proceed for the calculation. Door and window remain same, 0.65 multiplication. Ceiling is now different, because now this 0.02 which was plastered, which gives me 9 meter square Sabine, is now 0.3. So, 450 into 0.3, that is 135 Sabine. I have not treated the floor. So, it remain as it is 54, but there is again change in the wall. There is no change in the acoustical coefficient of the tiles, which is 0.45, but there is a decrease in the surface area of the tiles, which was 493, now it is 403, almost 90 meters square of the reduction in the area. So, I got almost 181.85, which was earlier 221. So, now my new total absorption of the room is 400, almost 401, 409 meter square Sabine, if you add this all. Now, let us calculate, and if you calculate with the same half full audience and the cane chair, this is 61.5 plus 400.9, 462, and if you divide that and use that one for your calculation, and please remember the volume is also changed, it is not 2700, it is 2250 now, and now your reverberation time is 0.8. So, which was 3.2 in the base case, untreated case which was now 1.15 in the case 1, now it is 0.8. So, let us draw a graph for that. The case 1 base case was 3.2, very high, all surface untreated. What happened next? The case 2, wall is treated and curtains and all these things are given in the base, in the doors and the windows, and wall is treated 1.15, and finally, in the case 2 it is 1 meter drop of suspension ceiling and wall and these things as previous treated suspension ceiling, it is 0.8. Probably we can adopt that for a lecture room or so. So, there are how to determine this application of the RT from that point of view, how to determine the sound absorption coefficient of the panel. Suppose I want to test a panel and I want to find out what is the alpha value of the panel is. So, how to test it? So, by with these equations and all. So, suppose I have a room and this room is empty and this empty room gives me RT1, this is the first condition. So, I can find out the S alpha by virtue of just change this particular, rearrange this particular equation. Now, what I did? I put a additional acoustical tiles, additional panel in that particular panel I am going to test. So, the RT value will going to change because there is a new addition of material. The A is the new the area of the material, and alpha new I am interested in how to find out what is the alpha of this particular panel. So, again I rearrange this equation and this, now I replace this S alpha here and I can easily find out the equation from this equation. I did is that this S alpha I have replaced here, and then I can rearrange the equation and the alpha nu of this particular panel can be found out if I know the RT1 and RT2, if I know the volume of the room, and if I know the area of this new panel. I do not need any else, anything else. I do not need the alpha of the room walls and all the surface areas and all. I can have some other methods also. Suppose I know that one material which is I have drawn here as a blue, and this particular value is alpha 1 of this particular material is known to me. Suppose I know this material, what is the value is known to me, and I found out the RT by this equation. This is the total S, that is the total surface area, minus A into alpha plus A into alpha 1, because I assume that the rest of the area is having the alpha. So, the rest of the area multiplied with the alpha, and this blue area which is the A is alpha 1. So, this gives me the total absorption and this RT. Next, I replace this by another material, another same area by another panel, the red in color, and this alpha 2 of this new material is unknown to me. So, I can rewrite this equation by RT2, I will get some different RT, and this is alpha 2. Now, you just rearrange this equation, because the S alpha minus A is common for everybody, this one S alpha minus A, and then you can rearrange and finally you can calculate the alpha, you can calculate the alpha 2 from this equation by this rearranging these things. Now, there are way to handle this particular scenario. My understanding is that I, being a designer, being a acoustical designer, I have to provide some RT or some design RT for a particular room. And when I got a particular room or a hall, it is all reflective surface, plastered surface and all reflective surface. So, I have to render it with some different material, and finally, I have to propose some material, and finally, I have to give some kind of the RT, I mean achieve some RT value. So, if you remember this graph I have drawn in the very first slide today, and These are the absorptions, room absorption, total room absorption, which is S alpha, and in x axis is the volume. So, this green line indicate, or maybe this red line indicate the RT value is 1, and this blue line indicate the RT value is 0.5. Suppose I am targeting 0.5, I am targeting to achieve 0.5, and my present value of RT of this room suppose 1. So, I have to reduce the RT value. How to reduce? From this particular graph, I can go from red to blue by virtue of a horizontal shift, and if I go with this is my option 1, I have to reduce the volume. See, I have to reduce the volume from 4000 to 2000. Another interesting point you see, if I want to go from green to red, same see the difference is 0.5 second, I have to go smaller, but if I want to go from 1 second to 0.5 second, same, the difference is again same, I have to go higher. So, when you go towards the lower part of the reverberation time, you have to give more effort, more rendering, more absorption. But in this option 1 is reduction of the volume from this to this is sometimes not possible. Why it is not possible? Because the volume of the room and the dimension of the room is basically comes from the occupancy, the rows, number of rows, the size and the leg space and the chair and the table and lot of other furniture details, and the prime factor is some kind of a circulations, and there are some the occupancy requirement and all. So, sometimes, and also the other dimension, the aspect ratios of the hall also. So, sometimes or probably many times it is not possible to reduce the volume and achieve that. So, the option 1 is not practical. So, how to touch this blue line from red line? The another way, if you go vertical. So, if you go vertical also from this 4000 in rather decreasing the volume, you can also touch. But what is this? You have to increase the room absorbent. So, from here it is almost 620 or something like that, or maybe 650 to almost 12,000 plus. So, how to increase the room absorbent, and what is room absorbent? S alpha. You cannot change S mostly, or what we can do is that we can increase the value of alpha. How can we increase the value of alpha? We can introduce some kind of acoustical tiles. Of course, if you do that, it is required money, because you have to render it with some different acoustical material, it required cost, and so you have to be careful also, I mean how much is actually going to achieved or so. So, there is this is the option 2, the increase of the room absorbent also give you reduce your particular RT. There is a third option also. You can touch this particular blue line from the red line by going angular. What does that mean? Going angular means actually I am increasing the room absorption and parallelly I am decreasing the room volume. So, if you decrease the room volume and increase the absorption, which was my last case, by creating a false ceiling, I decrease the volume and I render the surface with the room absorbent, these two also going to help me. So, again if I go back, there are 3 options to achieve a particular design RT. Either you reduce the volume, which always not going to be possible, you increase the room absorption, which is a bit costly of course, but mostly we do like that, or sometimes we can increase the volume, we reduce the volume and increase the room absorbent, which may be come into a most practical scenario. So, we are almost or maybe at the end of our lecture number 10. So, as usual we have some kind of homework for you. So, I have given just a single problem, calculate the reverberation time of a room which is empty condition, there is no furniture, no the audience, for the following data. The dimensions I have given, and all surfaces having a sound absorption coefficient is 0.1. So, again you can expect a very high reverberation time for as an answer. So, I have further the same problem is further extended, like what should be the sound absorption coefficient of that need to be provided only in the ceiling to get the reverberation time 1 second. So, definitely in the first problem I will get reverberation time more than 1 second, and so I want to make it 1 second. So, then only I am going to treat the ceiling surface, only the ceiling surface. So, what will be the alpha value of that particular tiles I need to place in the ceiling, that is my question. So, at the end I hope you have learned about the room acoustics and understand the basic principles of the room acoustics in the first 2 lectures. The third lecture you understand probably the way we handle the reflections and the absorptions, and we define the reflection coefficient, the sound reflection coefficient of any panel or any kind of material. And finally, in the last 2 lectures we discuss the concept of the reverberation time, and methodology or the formulation how we can actually calculate the reverberation time, and we design for reverberation for a particular room. So, the next week we will start the acoustical material, various type of acoustical material, and Dr. Sumana Gupta will deliver her lecture on that. Thank you very much.